Hello and welcome to the week 2 lectures on this course. And in the last week's lecture we discussed some set theory and logic, and starting from this week we will look at the mathematical definition of a topological structure or a topology. So remember that from our introduction, recall that a topology, the subject of topology studies properties of mathematical objects which remain unchanged under continuous deformations. So if you remember, we gave the example of a circle and a square, and we said that the interior, we call the interior space of the circle and square as holes, and under continuous deformations both these things have just one hole, right? So if you just deform the circle to some other object, some other shape, something like this. So continuous deformation means that you cannot break any part of this circle, so it cannot be it cannot look like this, for example. It cannot look like something like this. So there should not be any gap. Okay, so this is not allowed. So when you deform the circle, you get some space, some curve, closed curve like this, and still the number of hole is again 1. Okay. Similarly, you can deform the square to some other shape, say something like this, where you have this. Okay, so then again your number of holes remains the same. So under continuous deformations, this property remains unchanged, that the number of holes are the same. So this is the kind of properties that topology studies, and the main ideas of topology come from the study of real numbers, and continuous functions. Say continuous functions from the real line to itself. So we will see that we can define continuous functions once we have a concept of a topological structure. So let me begin by defining what is a topology or a topological structure on a set X, and for this I will use the following notation. So if X is a set, we denote by Px the power set of X, which is the set of all subsets of X. So a member A is in Px if and only if A is a subset of X, including X itself. It could be X itself, and it could also be the antiset, and all these things are inside this set, in this power set P of X. So let us define what is a topology or a topological structure. So whenever I say topology, I mean a topological structure. So what is the topology on a set X? So let X be a set. So of course our main examples will be of non-empty sets. So we can assume from the beginning that X is non-empty, and a collection of subsets which I will denote by this letter tau, which is a sub-collection or a subset of the set, the power set of X. So again, each element of tau is a subset of X. So a collection of subsets tau is called a topology on X if it satisfies the following properties. So let me go to a new page for this. So the first property that it should satisfy is that the empty set phi and the set itself X, they are in this collection tau. Okay, so of course the empty set is a subset of X, as we saw. The empty set is a subset of any set. So in particular for this set X, the empty set is a subset, and what we demand here is that the empty set as well as the entire set X should belong to this collection tau. The second property that it should satisfy is that if u1, u2, un are elements of tau, then the intersection, okay, so this is now a finite intersection, which I write like this. So this is just u1 intersection u2 un. So when I write I equal to 1 to n, it just means that the intersection takes into account all these sets u1, u2 up to un, and this must belong to tau. So we say that tau is closed under finite intersections. So whenever you have a finite number of sets which belong, so it is important that all of these sets must already be in tau, then the intersection must also belong to, finite intersection must also belong to tau. The third property that it should satisfy is that if u alpha in J is any indexed family of sets in tau, so all of these u alpha are in tau for all. So this is for all, sorry. So this symbol means for all alpha in J. So we have an indexed family of subsets of X, u alpha, each of which are in tau. Then the union alpha in J of u alpha, this is also in tau. So here notice that I took an arbitrary index set J, but here in the second one we only had finitely many sets. So here J can be infinite, countably or uncountably infinite, and we ask that, so again we say here that tau is closed under arbitrary unions, and that's all. These are the only properties that we need to define a topology on X. So what is a topological structure or a topology on X? It's just a collection of subsets of X which must satisfy some properties, and these are the three properties that one needs in order to define a topology on this set. So a notation or a terminology here that we will use all the time is that if a subset U is in tau, we call U an open set. Okay, so any member of tau is called an open set, and this is this of course comes from the example of real numbers, where you have open intervals of this form a, b, and one can, well, as we will see later on, we can define a topology on the set of real numbers for which these open intervals are exactly the open sets. Okay, so this terminology is coming from the set of real numbers. So this is one terminology, and another terminology that we will use is that we will call the pair X along with this collection of subsets tau, the topology. We will call this pair a topological space. Topological space. If the topology is clear from the context, topology tau is clear from the context, we say that X is a topological space. And it is this second one that we will use more often. Rather than saying X tau all the time, we will just say that X is a topological space. Okay, so let us see some examples of topological spaces. Example. So the first example is, suppose you have a set X as set, and we can define tau as simply the collection of the empty set as well as the set itself. Okay, so tau consists of only two sets. One is the empty set and the other is the entire set. Okay, so this is a sub collection of the power set of X, of course. And so let us check one by one whether it defines a topology on this set X. So the first property that we should check is that whether phi and X belongs to tau, and of course this is true. This is how it was defined, so this is true. The second one that we should check is that if you have u1, u2, un are in tau, then the finite intersection of all these ui's should belong to tau. Now let us see what are the possible options we have to choose these open sets. Of course, ui is equal to either phi or X, right? So for example, if u1 equals phi and u2 equals X, then u1 intersection u2 is empty and so belongs to this tau. Okay, so because the empty set is included and the intersection of the empty set with any set is empty, so it belongs to tau. Similarly, so this is just as an example. So similarly, since ui can be either phi or X, we have something of this form where either all sets are X. So let us divide it in various cases. Okay, so the first case is that if ui equals X for each I in the set 1 to up to n, then the intersection of all these I equal to 1 to n This is just x intersection x intersection x intersection x n times. Okay, so then of course x, and for any set x intersection x is equal to x intersection x is equal to x for any set. So this implies that this is the intersection of all these sets is the set x itself, and therefore belongs to tau. So in this case, when all the sets are equal to x, then the finite intersection property holds. What I mean by that is that the tau is closed under finite intersections. Another case is that if ui is empty for all I, then we have that the intersection again is just phi intersection phi n times. The same thing, except that now we have the empty set, and of course this is again the empty set, so this also belongs to tau. And thirdly, so this is the second case, and the third case is that when you have mixed values, like our previous example, one was phi and the other one was x, and the intersection was phi. So notice that if at least one ui is the empty set, okay, so ui is the empty set for at least one I, then the intersection of all these sets will be empty. Why? Because you can write this, so this is because we can write intersection of these sets ui to be intersection of all sets which are different from this particular value of the index for which it is empty. So suppose that this holds for I equals some I0. Okay, so then we can write the intersection I equal to 1 to n, but I not equal to I0. Okay, so this is one part, intersection with ui0 which is empty. Okay, so then we have, this is of the form A intersection phi, where A is any set, so this is our A here, A is any set, and we have the intersection with the empty set, so this must be empty. Okay, so this is because since A intersection phi is empty for any A. Okay, so in this way we have shown that either all of them are empty or all of them are x, or we have at least one which is empty, then the collection is closed under finite intersections. Similarly, so let me go back to this property that I wrote, and this is also true. We have verified that this holds. Similarly, we have to check that tau is closed under arbitrary unions. So if U alpha is a family, is an indexed family, of in tau, in this topology tau, then the arbitrary union of all these sets U alpha should be in tau. So again we can divide this in three different cases, where first is that if u alpha is equal to x for all alpha in J. Okay, then what happens? So we have only x's, so the union of all union of x over alpha in J, but this is exactly the set X. Why is this true? Well, yeah, so let me show. So I claim this, and we can use the definition of equality of two sets to show this. So first I will show that X is a subset of this union X. So for this, take, so first, to show that X is a subset of this union, take any x, small x in X, and then we have to show that this X belongs to this union. So what is this union? So u alpha, remember that this is the set of x's in X such that X belongs to u alpha for at least one alpha in J. Alright, so here of course all these u alphas are exactly equal to X. So we have seen that in this case all these u alphas are X, so therefore you can choose any alpha and X belongs to that set, since X belongs to u alpha for all alpha in J. So we wanted for at least one, but we actually see that in this case it is true for all alpha. This implies that X is a subset of this union. So I'm writing sometimes union alpha belonging to J u alpha, and sometimes I'm writing X because I've supposed that u alpha equals X for all alpha. So these two things are actually equal. So we have shown that X is a subset of this set. Now to show the reverse inclusion, X is a subset of this, again take, so to show, we take an element X in this union, and this implies that X belongs to X. Well, this is u alpha, remember that this is the same as u alpha. X belongs to X for at least one alpha in J, and this implies that X is in X, and so the union is a subset of X. So of course in general, if you have any subset, any collection of subsets u alpha, not just one for which every u alpha is equal to X, in this that's the case we are dealing with, but in general we have that if all the u alphas are subsets of X, then the union, arbitrary union, is a subset of X, okay, for any indexed family of subsets of X. Okay, so of course in our case all these u alphas are already equal to X, so this is the second one that we wanted to show is also true. So therefore we have X is equal to the union of all these sets u alpha for which they are all equal to X, and so of course X belongs to tau, so our arbitrary union in this case also belongs to tau. Now another case is that, case 2 is that when u alpha is empty, okay, for all alpha. So when u alpha is empty for all alpha, we have that the arbitrary union of u alphas is also empty. So this is what I claim. So we have to show that the union of all these u alphas is empty. So let me prove this by contradiction. So suppose that the union of these u alphas is not empty, and then we will show that this is a contradiction to the fact that all these u alphas must be empty. So because it is non-empty, we can choose an x which belongs to this union, okay, which means that x belongs to u alpha for at least one alpha in J, but this means that u alpha is non-empty. Okay, so let's say this is alpha 0. Okay, so alpha equals alpha 0. This is x is in u alpha 0, which means that u alpha 0 is non-empty, and this is a contradiction. Contradiction to the fact that u alpha 0 must also be empty. This is our assumption here. And so the arbitrary union of all these u alphas is empty when each of them is empty. Lastly, we have case 3, which is a collection u alpha where u alpha is either phi or x for each alpha. Okay, and when you take the union, so when you take the union of these u alphas, then you can break it up. We can break this union into two different unions. So first one is let's say beta in J1. This is a different index set, u beta, union, another union gamma in J2, u gamma. So what are these subsets J1 and J2? So J1 is the set of elements alpha in J such that u alpha is the empty set. So because u alpha can either be empty or x, so the first one is taking all these indices for which it is the empty set. Similarly, J2, of course this J1 is a subset of J. Similarly, J2 is the set of indices for which u alpha is x, right? And so when you take the union over J1 of these u betas, it means that all these u betas are empty, are the empty set. And we have seen already from case 2 that this is empty. Similarly, you have the u gammas from J2, the union over J2, and this must be the entire space X from case 1. And so we have the union of two different sets. One of them is phi and the other one is X, right? And then we can use the fact that union, so let me first write that the union of u alphas is the union of phi and X, and this is nothing but X itself. Okay, so the union of any set with the empty set is that set itself, and so this is also in tau. So we have seen that the collection tau, so let me go back to the definition of our collection, not here, sorry. So let me go back to the definition of our collection tau, which is just the collection of the empty set and the entire set X, and we have shown that all these properties that we want for a topology are valid for this collection. So this defines a topology. This is a topology on X.